All right, let's do 2 examples on hypothesis tests. So a current antacid provides relief for 70% of the people who use it. And we have a pharmacy. All right, this is pretty similar. All right, they run a study with 100 randomly selected patients and 75% experience relief. Is this evidence that the new drug is better? The hypotheses. We have the null hypothesis and the alternative hypothesis. This null, that's the assumption or status quo. And the alternative hypothesis is what we want to test. So let's look at this. What's the status quo? The status quo is the old drug, right? Status quo is that 70% will experience relief. And what we want to test is this new drug better? All right. So what we want to test is this new drug better than the old drug? And the status quo is that old drug, that old situation. Those are our null and alternative hypotheses. Can we use the central limit theorem? Can we use sampling distribution of proportions in this fashion? We have to check independence. As long as our sample is less than 10% of the population, we're good to go. Well, it's 100 randomly selected patients. Yeah, that's going to be less than 10% of the population, right? I can guarantee the population is bigger than 1,000 people. Okay. So yes, less than 10%. All right, we have 100. That's less than 10%. We're good to go. Randomization. Well, it says they're randomly selected. Da-da-da. Check. Success failure condition. Well, that checks n times p and n times q. And again, we don't know p. We don't know q. We're assuming that p is equal to this p naught. And we're assuming that p is about 70%. So we're going to use that for our check. Okay. So 70% times 100 people, that's 70. 30% times 100 people, that's 30. And these are both at least 10. We have to make sure that these are both at least 10. And we have them. So yes, this tells us immediately that when we take a sample, our sample proportion is going to be normally distributed or approximated with a normal distribution with mean of P naught. Hold on, let's use these letters. And again, this is our P naught. Our P naught is our assumption. Mean of P naught and standard deviation, P naught, Q naught over N. Set up the sampling distribution of proportions and find the test statistic. Well, we're almost done. Sampling distribution, P hat, normally distributed with mean P naught, our assumption, our status quo, 70%. What's our standard error? 0.7 times 0.3 divided by the square root of 100 inside of a square root. Oops. 0.7 times 0.3 divided by 100 is about 0.0458. What this means is that every time we take a sample, assuming that this drug has a 70% effectiveness rate, then on average, every time we do a sample, about 70%, it's going to be effective, plus or minus about 4.5%. Okay? That's our sampling distribution. What's our test statistic? In general, to get a z-value for something, you look at your data point, you subtract the mean, and divide by the standard deviation. What's our data point? Data point's that p hat. What's the mean of this sampling distribution? 0.7. Standard deviation of this sampling distribution? 0.0458. p hat. What is our p hat? P hat is the result from our survey, our sample. So in our sample, 75 out of 100 experienced relief. That's going to be 0.75 minus 0.7 over 0.0458. Our test statistic here, our z value, going to be 0.75 minus 0.7 divided by 0.0458. About 1.09. So on average, 70% are going to experience relief given our assumption, assuming our assumption is correct, plus or minus 4.5%. And in our specific sample, we're a little bit more than one standard deviation away from the mean. So that's what we needed to do in step 3. For the p-value, there were 3 tests: the left-tailed test, the right-tailed test, and the two-tailed test. In order to choose which test, we look at our alternative hypothesis. So this is going to tell us we want a right-tailed test. Okay, so we scroll up and say, okay, what was the right-tailed test again? The right-tailed test is what we use when our alternative hypothesis is p is bigger than or equal to, bigger than. And the p-value is just the probability that a standard normal random variable is bigger than our test statistic. Okay, our p-value is the probability that a standard normal variable is bigger than our test statistic, which is 1.09. This is the probability that if our assumption is correct, our probability that if the status quo is true and that 70% experience relief, what's the probability that we got so many, 75% in our case, just by random chance? If this is a really high probability, then yeah, it's random chance. Our assumption might be correct. If this is a really low probability, then, oh, it's probably not random chance. Our assumption's probably wrong. Okay? So this probability that a standard normal variable is 1.09 standard deviations above the mean, standard normal, 1.09, 13.79%. It's not super common, 14%, but this is bigger than alpha. If the p-value is low, the null must go. Well, this is not low. This is bigger than alpha. Alpha, again, in our case, going to be 5% since we didn't specify. So our conclusion is we don't have enough evidence to reject the null hypothesis. The p-value is low, the null must go, but we don't have that. So we're going to start by saying there is not enough evidence to reject the null hypothesis. What was the null hypothesis? Let's interpret our answer. There's not enough evidence to suggest that this new drug is better. It looks a little better, right? In our situation, it was 75%, and our status quo is 70%, so it looks better. But there's not enough statistical significance to this improvement with our sample size. We only sampled 100 people. Okay? In other words, so there's not enough evidence to claim our new drug is better, even though it was better in our sample. Even another way to interpret this is there's a 13.79% chance of getting these sample results are better. Assuming our new drug is the same. the same effectiveness. So specifically, the old drug has a 13.79% chance of getting these results too. So it's not enough evidence to claim it's better. Pause the video. Try to follow these same steps for this next example, okay? And see what you get. A company develops what it hopes will be better instructions for customers to set up their smartphones. The goal is to have 96% succeed. The company tests the new system on 400 people, and it was successful on 376. Is this strong evidence that the new system fails to meet the company goal? What are we trying to test? Step 1, set up hypotheses. Well, status quo, assumption, is our null hypothesis. What we're trying to test is the alternative hypothesis. The goal is to have 96% success. What are we testing? We're testing to see, look at that last sentence, we're testing to see if we're falling short. This is what we're trying to test. Those are our hypotheses. Can we use the central limit theorem? Well, we're going to have to check independence. The company tests a new system on 400 people. Yeah. If this is a real company, the population, the number of people buying their phones is going to be more than 4,000. Population is going to be more than 4,000. Right? For independence, we have that as long as we're less than 10% of the population. Randomization? It doesn't really specify randomness, but we're going to assume this. And success failure. What's n times p? What's n times q? Hopefully these should be at least 10. We're doing it on 400 people. So 400 times 0.96 and 400 times 0.04. Using the assumed probabilities here. So 384 are expected to succeed, and 16 are expected to fail. Again, it's kind of close, but again, we still are expecting at least 10 to fail and 10 to succeed. So the success failure condition is satisfied. Our three conditions are satisfied right here. The expected was 384. Turns out 376 is how many were successful in our test. Step 3 is I hope I'm remembering these steps right. It was the sampling distribution and the test statistic, right? Yeah, there it is. Great. So p hat is going to be normally distributed with mean p naught and standard deviation p naught q naught over n. Every time we do this test with 400 people, our average is going to be our assumption, assuming our assumption is correct, and we're testing whether our assumption is correct. So it's kind of weird in a sense that we're testing something using information from our assumption. Then go off to the side and calculate this. 0.96 is 0.04 divided by 400. Square root of 0.96 times 0.04 divided by 400. The standard deviation for the sampling distribution is 0.0098. Or in other words, we're assuming that on average, 96% are going to pass, plus or minus 1%. So one way of thinking of standard deviation is that most people are going to be within one standard deviation of the mean. Empirical rule says about 68% are within one standard deviation. So 68% are within 1%. 95% are going to be between 2 standard deviations of the mean. And again, a standard deviation here is about 1%, 1 percentage point, and 99.7% within 3 standard deviations away from the mean. So our test statistic is just going to be our z value. What was our p hat here? 376 were successful. Our p hat is 376 out of 400. What is that as a fraction? Our test statistic was only 94%. So we're testing to see whether we failed. And yes, 94% is less than our goal of 96%. Yes, we're lower than our target, but is this statistically significant enough to say that, yes, we're confident that we're failing our goal? Because we didn't test everyone, right? We didn't test all of the customers. We only tested 400 of the customers. Is this enough to conclude that we have failed our goal? Or is this within the range of normal probability, the range of reasonable doubt? That's what hypothesis testing is all about. So to calculate our test statistic to see how many standard deviations this is away from our mean, we use that formula, 0.94, subtract the mean, and divide by the standard deviation for this normal distribution. And our z value is going to be 0.94 minus 0.96 divided by 0.0098, I believe. Yep. Negative 2.04. Ooh, this is looking bad. Why is this looking bad? We're hoping this is close to the mean. This is over 2 standard a little over 2 standard deviations below the mean. 95% of the data is within 2 standard deviations. So if we're below 2 standard deviations, it's not looking good. Step 4 is looking at the p-value. Which test are we using? Left-tailed, right-tailed, or two-tailed? Look at the alternative hypothesis. Alternative hypothesis is going to tell us we need to use the left-tailed test. And again, you could look at that box to see exactly what that entails in the earlier notes. Or you could say, okay, our p-value is the probability that a standard normal variable is to the left, because we're using the left-tailed test, of negative 0.024, negative 2.04. This p-value, most important part of this whole section, this p-value is the probability that, assuming everything is correct, assuming our assumption, assuming our null hypothesis, assuming that 96% of customers are figuring things out, the probability that our sample could return something at least this bad, right? 94% is under our target. What's the probability of doing a sample and getting at least this bad or worse? If this probability is high, well then yeah, it's very probable that we just get unlucky. If this probability is low, if it's very rare to get something this low, then we probably messed up. Our assumption's probably incorrect. We're going to throw out that null hypothesis. If the p-value is low, the null must go. So what's the probability that a standard normal random variable is less than 2.04 below the mean? Oops. Less than negative 2.04. Oof, about 2%, 0.0207. There's a 2% chance to get this unlucky, assuming that our null hypothesis is correct. This is less than alpha. It's less than 0.05. It's less than 5%. If the p-value is low, the null must go. So there is sufficient evidence. There's sufficient evidence. And again, I'm just going to save ourselves a little work, right? This means we reject the null hypothesis. What was our null hypothesis? Because there's significant evidence to reject it, whatever it is. We're rejecting that null hypothesis. The null hypothesis was our goal of 90% of 96% of customers succeeding. So our target fell short, and we're saying that this is enough evidence to reject the null hypothesis. Let's use a little bit better words. Enough evidence to claim our goal of 96%. English really comes into play here, not math. Evidence to claim our goal of 96% is not being met. Again, it doesn't necessarily matter that our sample is below the goal. What matters is how likely it is that our sample is this far below the goal. Statistics, probability, it is random, is not being met. And that's kind of the main stuff. You could interpret it a little more by say, right, if it were being met, there'd only be a 2% chance of getting something this bad. If it were being met, if our assumption was correct, if our null hypothesis were true, there's only a 2% chance, our p-value, of getting survey results this bad or worse. All right. And that's what hypothesis testing is all about. In the next video, we are going to kind of compare this with confidence intervals. But that's all for now.